All right, so now we're going to talk about the Riemannian Hessian operator. And as you might expect, the main motivation for doing this is that if you're trying to develop an optimization method, in particular the Newton method, then that's really based on constructing a quadratic model, it's like of the cost function. Okay, so so the motivation, if you will, it's like for studying, it's like the Riemannian Hessian operator is to ultimately construct some sort of quadratic model, it's like of the cost function. So this is motivated by the desire to construct a quadratic model of the cost function right, with a view towards applications to optimization. Okay. So as is sort of what we're apt to do, we're going to try to first understand, well, what are some of the properties of the Hessian operator? It's like one would like to respect. You know, oh, well, what are properties of the Hessian operator? It's like in Rn, it's like which would then like to express in our generalization. It's like to Riemannian manifolds. Okay, so you're given. So let's consider the case in sort of Rn first, just as motivation, right? So you have a function. So you're given f, right, which is a real valued function on Rn. And of course, you know that this is just classically defined. The Hessian associated with the this real valued function is classically defined to be just a n by n matrix. It's like whose entries have involved the mixed partial derivatives of that function, right? So so sort of del squared, it's like ij of f at some point, right, is usually given by this mixed partial derivative. Okay, and so so if you want to generalize this to manifolds, then what you should think of is that you want to think of it as a operator, if you will, right? So one way to view this geometrically is as a linear operator. It's like from you know, some Euclidean space to another Euclidean space. Okay. All right. So how should I write this? Right. So the Hessian, okay, of f of x, right? So you think of this now as an operator. It acts on some vector. Let's call that z. Okay. Let's just define it to be the following, right? So it's the sum over I and j of this object, right? You should think of as, and then there's a representation, if you will. It's like of this x1 to xn cj ej. Okay, so let me just try to explain this, right? Where these ej's, ei's, it's like basis, right? It's an orthonormal basis. For E, right? That's That's to be expected, right? Because you have a linear operator acting on a vector and you want to get another vector out of it. So that's the basis by which you're expanding that vector. And then this thing here is sort of a bunch of coefficients, right? So z is going to be, so the z super I, as you might expect, is the coordinates with respect to this basis, right? And sort of z is equal to zi, zj, ej summed over j, right? And f hat x1, sorry, x1 to xn, right, is just defined to be f evaluated at x1, e1, xn, en. Okay, so that's sort of, all right. So the way to sort of think of this is that essentially what you're doing is that you are choosing an orthonormal basis for this Euclidean space, and then f hat is the local representative with respect to the coordinates associated with that coordinate, with respect to the orthonormal basis. Okay. Okay. So, and you can check that this is independent of the choice. Well, what I mean is that this operator, right, Hessian f acting on another vector, is independent of the choice of orthonormal basis. Okay, all right. So alternatively, it's like instead of writing it in this way, you can also sort of ask, it's like what properties it's like the Hessian operator has, and so you can also formulate it in terms of two properties. Sort of equivalently. Right, we can characterize sort of the Hessian of f, right, by the following properties. Okay, so the first of which is that Hessian f of x acting on a vector y, right? So this gives me some other vector paired with y itself via some inner product is equal to d squared f of x acting on y, right? Which is defined to be d squared dt squared, right? F of x plus ty, okay, evaluated at t equals to 0. Okay, all right. Okay, so this is essentially the second derivative of the function. It's like where you take the function and you think of it just as moving. It's like in starting at a point x. It's like in moving in the direction y, right? Okay, and the second thing is that okay, so this is just what's happening. It's like along that vector, and then if you take the Hessian of f of x and you act it on y, but you pair it with a different vector z, right? This has a symmetry property. This is y paired with the Hessian of f of x, z acting, okay, acting on z. So, so again, if you think of this as a matrix, right? This is saying something like a times y paired with z is y paired with a acting on z. Okay, so that's of course the usual notion of symmetry, sort of a symmetric matrix, right? So this is symmetry. Okay, So, all right. So the point is, in any case, is that you can, these are some properties, if you will, it's like of the usual Hessian matrix, right? But now viewed as a linear operator, right? As it's apt to do, it's like when you have a matrix, viewed as a linear operator, it's like from some Euclidean space to itself, okay? And you can again either characterize it, it's like in this way, or sort of more abstractly in this way. And with that in mind, now we'll try to describe for you what the Hessian operator is then on a Riemannian manifold, okay? Which again, it's like it's meant to generalize these properties. Okay, so let me just stop here for now.